This is Kate from the Learning Center, Success Center. Change their names every now and then.
Yeah. Hi, everybody. I just wanted to come by and make sure that you know about one of the great services available for you on campus, which is the Success Center. It is my job to sit in my office and wait for students to come in and ask me questions. So if you're stuck on anything, you can just come on in and ask, and I will help you out. If you're taking any other science classes, you can come in for help with those as well. If you haven't been to the Success Center before, if you walk in the main doors of the library, you'll be facing the stairs. Walk towards the stairs, but don't go up. Veer to your right, and you'll be at the door for the Success Center. So to find me, you go into the Success Center all the way to the back, and around the corner, the first office is Josh. He can also help you with math, and mine is the second office with mushrooms on the door. You can't miss it. If you walk into the Success Center, you'll see it is set up with tables, so that's meant to encourage group work. And I do highly recommend you get a study buddy or a study group, because as soon as you start talking through problems or reasoning your way through, explaining how you got from one step to another, it will make more sense to you. So I recommend you do that. But whether you're working on your own or in a group, it is a good place to study, because if you get stuck on something, we are right there to help you. Josh and I are there Monday to Friday, 8 to 4. So you can use the Success Center as a study space anytime the library is open. If you need help with English or writing, either because you're in an English class or a communications class, or you're writing a report for something, we have help for that as well. When you walk in, the first door on your right is Shannon, and the door right after mine is Carolyn. And they can help you with all of that writing-y stuff, because I sure can't. So you can either scan a QR code on their door, or you can go to the Success Center website and make an appointment. So so you can see right there, it says book an appointment with Carolyn at the bottom, right there, or scroll down and there's Shannon's info as well. So they will take appointments to have time to go through your whole, whatever it is you're doing. But math and science help is all just drop in. So just come on in and ask a question whenever you're stuck. And I will add one more thing, and that's that if you're struggling in this class, I get it. I failed math a couple of times before I got to where I am. So I totally understand why it's difficult sometimes, and I understand how frustrating it can be if you're not getting it. So please, please, please don't hesitate to come in and help. Sometimes all you need is just hearing it maybe a little bit slower, maybe going through it step by step. Maybe you don't feel super comfortable asking questions in class, and you can't find Emily at the time. Just come on in and you can ask a question one-on-one in my office. If that's more comfortable for you, then please feel free to do that. And no, I really, really do understand the struggle of math, because I was there. Are there any questions? Okay, thanks. I hope to see some of you soon.
Awesome. Thanks, Kate. See you. And now you're done with me.
Yes, I am until September.
See you then. I should have asked her how many of these she's done so far. When I saw her on, I guess it was just yesterday, she was at 19. So same spiel, but okay. I did catch it in the recording, just making sure, so I'm not losing it here. You guys are so good and organized. Got a few people asking me, hey, am I missing something? Have you posted an assignment or something like that? And usually when I was a student, it was just kind of like, just don't poke the bear. But I do, I think it's really nice to see. So I was kind of holding off. One, we hadn't, covered a ton of material. And two, I was still kind of deciding on how I wanted to do the assignments. And so, like I mentioned, I haven't taught this course in a long time, so it's kind of my opportunity to change it up and have some fun with it. Maybe not fun, but kind of do something different. What I've landed on, because it does sound like people have been plugging away through these questions from the textbook. So we're in chapter 1 here, and what I've done is I don't have a pointer on here, I guess, but I'll use my arms. So for each section, okay, I've made a Dropbox where you can submit your answers to the even exercises. The reason I chose the evens is because I'll be posting, so I've made 2 of the solutions so far. Takes me time too. So so I posted the solutions to the odd exercises, but if you look at them, it's kind of like see one, do one, see one, do one, see one, do one, and they are very similar, right? And so so you can have a look. I encourage you to try the odd ones and then check against the solutions, and then you'll feel more comfortable, right? And then you can try the even ones, and the even ones are the ones to submit. I want to have them in one, preferably PDF file, right? If you've got a scanning app or something, usually we're just working on paper, you can scan it, compile it, and upload it. Question?
When we hand it in, if we get one wrong, are we allowed to resubmit it?
So I forgot to say it, but I'm only going to grade it for completion, okay? And so if I see a glaring mistake, I'll circle it, or maybe make a note of it in the feedback, but it still is considered complete. So even if you've tried it, that's all I'm looking for, right? Did you try all these things, right? And so I did it out of 10, just kind of, so you could get 7 out of 10 completion marks. And yeah, you are at my mercy. Do I think it's complete? Usually, you know, if you've tried it, then 10 out of 10, moving on, right? Because even I recognize that this would be a lot of marking, right? But I was kind of tempted to do kind of online assessments, and I will put together a review online one where you get feedback immediately and stuff like that. But because our test is on paper, our tests, both of them are on paper, it makes more sense for you to for me to see your writing and maybe kind of correct some behaviors if I see anything bad, right? Okay, so if you worked through some of those exercises, even if they're not just the even ones, I can obviously skip the odd ones. If you worked through all of them, you can just submit those. And so that's totally fine. Made them due a week from today. Okay. So kind of the first section is itty bitty, just a little quick one. And then 1.2 is also quite short. And so I'll give you more time for 1.4 and 1.5, but for now they're just set for next Thursday, but I'll bump it as we go. Okay. I tend to give just from the time that we finish a topic, I give you a week to do stuff, right? Okay. Any questions about that? All right. So completion marks, even better, right? Even closer to that 100% on the assignments. Like I said, I'm expecting you to have. Right? Maybe that's why everyone's chomping at the bit. I want to get 100. Okay. So today we start applications of lines, right? And so we built linear equations last day. I already asked, but any questions before we start applications? Okay. I guess I should do a smidge of review, huh? We talked about, so a little bit of review. We talked about, oops, sorry. the slope intercept form of a line. That's y is mx plus b. M, of course, is the slope. And b is the y-intercept. See if I can squeeze that on here. I'm just gonna go slope here. Can you see that? It's itty bitty. Yeah. So that was one form of the line, and usually my go-to, right? If I'm easily able to rearrange my equation into the form of y equals mx plus b, I find that's really useful because then I can see the slope clear as day, whatever is attached to the x, and then the b is wherever it crosses the y-axis, right? And so that's a kind of my go-to form of a line. The other form of a line that we talked about is the point slope. I mixed the names up, and I promised last day that you wouldn't need to memorize the names of these, right? If you need them, I'll give them to you. But the point slope form of a line was y minus y1 is m times x minus x1. I have to remember it. And then finally, we introduce the standard form, which was ax plus by is equal to c. And then we said, okay, if you have an equation in standard form, then where m is negative a over b. And we explored kind of why that would be. And it's because if you rearrange it and you solve for y, right, then what would you have to do, right? You've got, you're solving for this y, so you would subtract ax over to the right-hand side, so that gets shifted over, and then you would be dividing by b, right? So then your slope would be negative a over b. Nice. So like I said, main player here is this little guy, but it's useful to know the other two as well. When would you prefer this form of the line, the point slope form of a line? I would prefer it. I think it's a lot easier if you have one point and the slope, as the name kind of suggests, right? Because then you can just plug in your x and your y coordinates and your slope, and then you have your line, right? You can rearrange it if you want back into y equals mx plus b, but kind of a nice one to have up our sleeves. The standard form, although it sounds like it would be kind of the standard one, I don't find it's terribly useful, right? It's just kind of more work. More math work. Okay, so we had all these different forms of a line. Oh, I don't know what the name of this thing is. Like the end. Ooh, fancy. The end of the review is what I'm indicating. Okay. And I guess usually it has a proper, I wonder what those are called. Anyways, that's a rabbit hole. Okay. We ready for applications? So where would lines come up? Lines come up, and we model a lot of different relationships with lines, but definitely kind of financial situations. A lot of them can be modeled with lines. Okay? And so that's what we're going to look at today. Okay, some kind of, not really tips and tricks, but it's worth saying, read the problem carefully. I know that sounds stupid, but it's important. Right? You want to kind of read it carefully, slowly. You can highlight important information maybe not necessarily with a highlighter, but if that helps you, that's cool. I'd say most importantly, keep track of which values correspond to the independent variable. Now, the independent variable is your x. It's on the next line, but I want to have it. And your dependent variable is going to be your y generically. Okay? Because if you think about y equals mx plus b, right, usually what we do is we change x and we see, right, what changes in the y. We're able to do it in reverse, but traditionally, right, we change the level of x and then we see what the value of y is, okay? Which means that y depends on x, right? Whatever you find for y, it depends on what you plug in for x, okay? Making x the independent variable. Okay. First things first, we need to find the x and the y value, right? Kind of identify which one depends on the other one. The one that depends on the other variable is going to be your y. Okay. So let's read this first problem. I'll bump this down here. A taxi service, try to make it as big as I can, not that much bigger, charges 50 cents per mile plus a $5 flat fee. So you get in the cab all immediately, $5. That's pretty standard, right? Or some dollar amount, right? And so what will be the cost of traveling 20 miles? What will be the cost of traveling X miles? Okay. I would say that the cost depends on how far you traveled. That seems reasonable, right? And so here, let's say the cost depends on the distance. Therefore, y is going to be the cost and x is going to be the distance. That's going to be a good place to start. If we want to figure out the cost of traveling 20 miles, so then I have a distance of 20. If we let the distance be 20, we're going to start with the $5 flat fee, right? Kind of start to finish. I get in the cab, they charge me $5. So if we say the cost is that $5, just the flat rate. I'll make a note here. This is the flat fee. All right. Get in the cab, $5. And then for every additional mile, and we're going to talk about 20 miles, they charge 50 cents. You could solve this problem, right? You don't need to sit down and figure out what your X and your Y's are, right? You could probably get there on your own, right? 50 cents times 20 miles, right? You're going roughly 20 miles, 20 kilometers, who cares? And so, right, you would take your distance, multiply it by 50 cents, and add it to the flat fee, and that would be your total cost, right? And so we're going to do that, right? So you do that in your head. Now we're going to translate it into a mathematical formula, a linear equation. But in this case, the cost is going to be 5 plus 50 cents times 20 is 10. So the total cost is $15 for 20 miles. Can do the same thing, right? The only thing for X miles is now I want to replace that 20 and I want to be able to plug in any number of miles and have just a cost function. So then, let's see here, sure. Let the distance equal X. Then I get the cost is still the $5 flat fee plus 50 cents times the X. And this is what we call our cost function. Yeah. If we replace the cost with the Y, just generically, or Y is 5 plus 0.50x, you prefer. Now it looks a lot like a line that we've been working with already, right? We have a y-intercept of 5, which makes sense, right? Because then if we are thinking about a graph of this thing, right? I have to start, let's say this is at $5. I start at $5 and then I have a slope of 0.5, right? And that's going to be the cost to the distance, right? Or the X and the Y if you prefer. Nice. So you have a slope of 50 cents or 0.5, 1/2. Any questions about that one? No, just an itchy eyeball. I was too quick on the draw. How about the next one? I'll make it a little bit bigger here, or as big as I can. The variable cost to manufacture a product is $10 per item. Yeah? And the fixed cost is $2,500 or $2,500, I should say. If X represents the number of items manufactured and Y represents the total cost, write the cost function, right? So here we're told X is the number of items and Y is the cost, which makes sense. The cost depends on the number of items, right? The number of items, I guess in a roundabout way, we could get there and we could argue that it depends on the cost, but right, but explicitly the cost depends on the number of items. So X is the number of items. I'm just going to use the X and the Y. So then Y, you could have written cost if you want, right? But because they've already defined it, let's talk in terms of X and Y. It saves us a little bit of writing too. So Y is the total cost. The total cost, you have to talk about your variable cost, it's called. The variable cost plus the fixed costs is the total cost. So there's going to be a variable cost if you're producing some product, right? And we're told that it's $10 per item. So then Y is 10 times X. right? Because X is the number of items. And then plus the fixed cost, which we're told is 2,500. If you, I don't know, make some product and you rent a space, right? Maybe rent is 2,500. You can't get away from it. Even if you don't sell anything, you still have to pay rent, right? So you could have, so your baseline cost is 2,500, right? And then for each item that you produce, right, it's also going to cost you $10 in materials or time or both, right? And so those would depend on how many items you are producing. Hopefully on the other end of this, we would also have a profit function, right? So this is the cost function, which is a straight line, right? So it costs money to produce things, but the more you produce, the more you're able to sell, and then the higher your profit is. And we'll explore the profit function and the cost functions in the next section. But they look a lot like this, and they are just straight lines. What about this next one? Sounds similar to start off with, but the information that we're given is slightly different. Okay. In this case, I would liken it to being given 2 points on a line, right? How is that? It costs $750 to manufacture 25 items and $1,000 to manufacture 50 items. Assuming a linear relationship holds, find the cost equation and use this function to predict the cost of 100 items. Okay, so first things first, we're going to figure out which one is our X and which one is our Y, right? And as before, the cost is going to be our Y, right? The cost depends on how many items we manufacture. And so let's say the number of items is X and the cost is your Y. That's kind of your first step in setting up these problems and solving these problems. If that's the case, I'm given an XY coordinate followed by another XY coordinate, right? So that's kind of the key here. So we've been given XY coordinates. When X is 25, the cost is 750. And when X is 50, the cost is 1,000. If you kind of ignore the word problem, and I just gave you these 2 points, and I asked you to find the equation of the line, right, that passes through these 2 points, we can do that, right? And so now we're kind of building on those skills, and we're saying, okay, if I have 2 points on a line, right, then I can do what? I can find the equation of the line by first finding the slope, right? Step 1, find the slope. Then step 2, find B, the y-intercept, and then you've got your line. But wait, there's more. We'll start there, right? But we were also asked to use this function to predict the cost of 100 items, right? Which is usually how we use these lines, right? We establish these lines and then we're able to predict, okay, well, what if I did 100, right? Then what would my cost be? And what would my profit be? More importantly, right? And then you're ready to go on Dragon's Den. And they say, oh, no, it already exists, thanks. Try again. All right, so now, first things first, find the slope. Oops, I need the slope. As a refresher is y2 minus y1 over x2 minus x1. It's always good, good form or good practice to write out your empty equation before you go ahead and fill it in, right? And so part of my goal is to develop good math habits. Right? And so that's definitely one of them. So writing out your kind of empty equation, show me what you will be filling in, and then you can fill it in. Doesn't matter which point you use as point 1 and point 2, right? We've seen this before, but I usually just use this first one as point 1 and the second one as point 2. Right, simple. Means I have to write them in reverse though. Right? And so 1,000 minus 750 divided by 50 minus 25. I'll write a little note here. Step 1, find the slope. Which is what we're doing. 250 divided by 25. Well, aren't they so nice? What does that slope tell us? Tells us the per unit cost, right? So this is the cost going from 25 to 50 items. We figured out, okay, the slope here, rise over run, is, this is the per unit cost. Put this down. So that's fun. What's the next step? Now that we have the slope, well, I guess you could choose your own adventure, right? If you go back to, you could use the point slope form of a line. You could pick one of those points. You have the slope already. I like to just stick with my trusty y equals mx plus b and plug in my value of x and my value of y, one of the ones that I know, right, that are on the line, and then solve for b. I'll keep doing that. You can play around with it. I don't know why you would use the standard form. Yikes, show offs. No, don't do that. You can if you want, but yikes. Okay. So next thing, we have to find the intercept. So if I have y equals mx plus b, then y is 10x plus b. And my second step is find the y-intercept, which is b, using one of the 2 points that we know have to be on the line, right? Using one of the points, of the known points, I should say. Okay. I'll use the first one. Doesn't matter, you can try it with the second one, right? They should both get you to the same value for b. So if y is 750 and 10 times what? 25 plus b. I have to practice writing my b's. All my b's look like 6s, and I don't know how to fix that. But I like to do like a really curled 6 for that reason. So you'll know. Or maybe not. 750 is equal to 10 times 25, puts me at 250. Plus B. So then B must be 750 minus 250, putting me at 500. Right? What's that? In terms of the costs and things, that's going to be my fixed cost, right? My phone bills and my rent and, well, wouldn't that be nice, right? We've got low fixed costs, so that's nice, right? Kind of a high per unit cost, in my opinion, but considering. But what's this? This is my fixed cost. Oops. So then y equals 10x plus 500 is my cost function. So find the cost equation. That's what we did. All right. And I'll label it. Are the lights flickering in here? Is that just me? Okay. I could have sworn. Okay. So that's the cost equation, or the cost function if you prefer. And then we're going to use this function to predict the cost of 100 items. So here, this is your cost equation. And now we're going to predict the cost of 100 items, which means that X is 100. Kind of pricey. So then Y is 10. I'll do 10x plus 500. So Y is 10 times 100 plus 500. Ten times 100. It's usually 1,000 plus 500. 1,500. Anything else they wanted us to do? No. Okay. Nice. Any questions? Okay. Nice. Maybe I'll bump this up a line. Like I said, these are all cost functions, kind of a bummer, right? Later we'll have profit functions. What do you think the profit function looks like? You can think on that. There's no fixed profit, unfortunately. I know, right? It's just going to be something that looks like this. Y is, usually we use P for the price that you're able to sell this item at, but it's still, X is still the number of items, right? And so your profit function looks like this, your profit function. It'd be really nice if you could just have some fixed profit, which means what? You don't even need to do anything. You just start off with some profit for the month. That's not how it works, right? And so that's why there's no y-intercept, right? You have to sell an item, get a cost or some dollar amount that someone pays for it, and then so on and so forth. I gave it away. I can't believe it. It's not even until the next section. I couldn't help it. That's what the profit function looks like. Which means we're going to have a line and a line, which are going to look like this. And so, or maybe like this, some point you break even. Right? And so, but we'll be able to graph two lines. We already know how to graph two lines on the same graph, right? You can just adjust your axes so it accommodates both, and then you're off to the races. And then you just need to find the intersection. I know. It's just down here. So close. Another common kind of conversion function is going between Celsius and Fahrenheit, right? A lot of our recipes are in Fahrenheit, because they're all in the States. And so I don't know about you guys, but my air fryer is in Celsius. I'm constantly doing it. I feel like, hey, Google, what's 400 Fahrenheit in Celsius? I should be able to do it, but a freezing temperature of water in Celsius is 0 degrees. We know that, I hope. And in Fahrenheit, it's 32 degrees. You may not know that yet until now. I'm telling you. And the boiling temperatures of water in Celsius and Fahrenheit are 100 degrees. We know that, and 212 degrees respectively, right? Depending on your altitude, but we're ignoring that. Write a conversion equation from Celsius to Fahrenheit, or if you prefer, from Fahrenheit to Celsius, it doesn't matter. The other, you just input one and output the other, and it doesn't really matter which one is the independent and which one's the dependent. Okay? And so from Celsius to Fahrenheit, and then use this equation to convert 30 degrees Celsius into Fahrenheit. First, we need to set up that equation, though. That's the hard part. What does this look like? To me, this looks exactly like the question we just did, right? That takes practice, right? That's not going to be obvious, right? But I have an XY coordinate and I have another XY coordinate, right? And so reading all these questions and mapping it back, oh, I've seen this before, right? I know how to solve this, right? That's going to be kind of the hardest part, I think, right? But just says here, right, I have an XY coordinate. In fact, I've been given 2. So then I need to find the slope, and then I find the y-intercept, and then I set up my line, and I can use it to plug in some value of X or Fahrenheit or Celsius, whatever we want. For simplicity, let's not use X and Y. Let's use C and F, right? And then it'll be kind of easier to move things around. Okay. Let's let this Celsius, wouldn't it be so funny if I let Celsius be F and Fahrenheit be C? Funny is maybe not the term. Cheeky. Okay. One of these has to be your X, another one has to be your Y. It doesn't matter which one is which, but let's say that my ordered pairs are going to be in the form of Celsius corresponding Fahrenheit. Right? That's probably the biggest leap so far. Right? It's kind of picking which one I want to be my X and then which one is going to be my Y. And then, and you're welcome to use F as your X and C as your Y, but it doesn't matter, you know, in this case. Okay, so we were given when the Celsius is 0, Fahrenheit is 32. Right? That's our first point. Right? And when Celsius is 100, Fahrenheit is 212. There. Hardest part of the question done. Right? The rest is just kind of getting used to these motions of finding the slope, finding the y-intercept, smushing them together, and then using that line. So nothing to it but to do it. Here we go. M is always y2 minus y1 over x2 minus x1. So I'll label it again, find the slope. You can see why we spent nearly a full night learning how to find the slope, right? Given 2 points, right? Because we need it. I'm going to start calling it night because it is. It feels like nighttime. But once we start creeping towards the end of March, it might still be light out when we finish. And isn't that going to be so nice? But for now, no. 212 minus 32. I don't know. My math's not that good. I also don't trust myself. 212 minus 32 is 180. I'll keep that in mind. And 100 minus 0. 180 divided by 100. I'm going to sneak it on here. I'm going to use the decimal version. You're welcome to use the fraction if you want, but you'd have to lug it around and ugh. I'm going to add a page here. So then the slope is 1.8. If C is your X and F is your Y, it would be different, right? If you had F comma C as your setup, right? You can play around with that. But let's keep going. So now, step 2, find the y-intercept. I'll start with a generic y equals mx plus b. So then we know m is 1.8 times x plus b. And just pick one of these points. I've got an x equals 0, so that's nice. So let's use that. Why is that nice? At 0.32 or 100/212. It's nice because then I have 32 is 1.8 times 0, which is going to go to 0 plus b. So then I have 0 plus b equals 32. So b must be 32. Nice. Okay. Now we can set up our equation. I used y equals mx plus b, but really, what should I have written? Fahrenheit and Celsius. I should probably write that in red because I did forget. Bad, Emily. But then we have that Fahrenheit is 1.8 times the Celsius plus 32. What if you had solve for C as a function of F? Now that we have this equation here, right? Then we can move things around and we can kind of make some changes. What would this be the same as? This would mean that if you had started up here, let's see if I can keep it all on the same page, and you had said, okay, I'm gonna let Fahrenheit be my X value and Celsius be my Y value, then I would end up with the function we're about to solve for, right? But you can rearrange this one that we found and get C on the other side and F on the right-hand side. So let's do that. F is 1.8 C plus 32. Solving for C now, I get F minus 32 is 1.8 times C. So C is F minus 32 divided by 1.8, which is, I'd say, not as nice, right, as what we found. But that's okay. And you can split those up if you want, but it makes it even messier. So depending on how you set up your X and your Y's, right, you can have this function. I called it a function of F. So C is a function of F. All that's saying is once I've solved for C, right, I can plug in a value of F, right, and the resulting C, I can solve for the value of C. And so that's what we mean when we say C is a function of F. You plug in some F and it returns the corresponding C. This was kind of an aside. So here, how can I'll just put a little box around it. Makes it look, oops, aside E. Makes it look important, but how can I make it look not important? How about gray? There, it's still boxed, so it makes it look important. It's not. Just wanted to throw that in so you have it. Okay. So this is the conversion equation, and if you Googled it right now, it would be what would pop up. And so it's true. And we're going to use this equation to convert 30 degrees Celsius into Fahrenheit. Okay, so I'm going to input C equals 30 and solve for F. Because I'm putting in a C and solving for F, I'll use this version of the equation, which is also kind of how I chose my X and Y, but you could do the same thing here, right? You could let this be 30, this C be 30, and then solve for F. That's okay. You get to the same results. So, find F at C equals 30. I think it was. Yeah. So then I'll use F is 1.8 C plus 32. 1.8 times 30 plus 32. Making sure you do that 1.8 times 30 first, and then add the 32. We get a nice 54 plus 32. So to show that I'm doing this multiplication first, then I write that out as a separate step. You don't have to, but it's more so that when you're reading my work, you're reminded, okay, I have to do that multiplication first, and then I can add. (86°F). It's nice to be reminded. Fahrenheit. Who knows? It's a mystery. Can't keep track of Fahrenheit. Nice. So 30 degrees Celsius is 86 degrees Fahrenheit. Ta-da! Now you don't need Google anymore, or whatever your kitchen device is. If you don't have one in your kitchen, I highly recommend it. Google set a timer. Freaking out. Okay. Any questions about that one? Or any of these? Okay. How about more applications? I can't believe they made a section called more applications. Okay. Makes it sound so daunting. We level up a little bit because, as I've kind of mentioned, sprinkled in there, right, being able to find the intersection of two lines is going to be pretty useful, right? And so that's where these two lines are the same, right? And so here, let's bump this down. And if I just kind of develop it a little bit here, let's say I have line 1 is orange. I'll call it line 1, L1. Doesn't matter what the equation is, right? Sum y equals mx plus b. And then I'm going to put line 2 somewhere here. It doesn't matter where, but it also has some y equals mx plus b, right? Different slope, clearly. If they had the same slope, what would they look like? They'd be parallel, right? Same slope, different intercepts. In this case, we have different y-intercepts and different slopes, right? Okay, so now the intersection, I think we're all comfortable with. This is the intersection, right? That's where they intersect. So where they cross. Okay, so this is the intersection. Just like roads do and everything. Okay. At that exact point, and only at the intersection, right? Line 1, let me zoom in here, and line 2 have the same value of x and the same value of y. Right? Only at that intersection. So our goal, if we're finding the intersection of two lines, is going to be, okay, find an xy coordinate that satisfies both of these lines. Right? So that's what we're going to do. Let's do it. I really undershot how much space I need. Can write a lot, I guess. Oh, no, don't move that. Okay. I'll just zoom in like this. So if we want to find the intersection of this line, y equals 3x minus 1, and a line at negative x plus 7, okay, how would you tackle that? We could draw them. Let's visualize it. Let's figure out what some plausible values are, right? Reasonable values for the intersection. That might be nice. Let's start there. We know how to graph stuff. Let's call this line 1. Can you see the orange in the back there? Is it kind of, I know, bad, but I'm running out of colors. Oops. Line 2. Maybe I'll do this. I'll turn it green. Oh. Not sure how that happened, but maybe I didn't do it purple. There. Green and purple, that goes nice together. All right. How do we draw a line? Or should we cheat and use Desmos? Ooh, tempting, right? No, because it'll give us the intersection. We'll use it to confirm. Let's sketch it out. I don't want you to graph it too seriously, but for line 1, what are you gonna do to graph a line? Pick any 2 values of x and solve for the y, and then you have 2 points on that line. I like to do 0, 1. Y equals 3x minus 1. Unless it gives me kind of terrible looking math, I always just use 0 and 1 and go from there. If x is 0, then I get y is negative 1. And if x is 1, 3 times 1 is 3 minus 1 puts me at 2. So then my xy coordinate is at 0, negative 1, and 1, 2 for line 1. I'm holding off on making a grid until I know what my xy coordinates are that I need to plot, because I need to have room for all of them, right? And so for line 2, I'll do the same thing. I'll let x be 0 and 1, and y is negative x plus 7. Negative 0 is 0 plus 7 is 7. So this point is at 0, 7. Negative 1 plus 7 is 6, so 1 and 6. So I need to make enough room on my y-axis to accommodate the 7, right? And negative 1. I use just values of 0 and 1 for x, so I don't need a ton of room on the x-axis, but I do need room on the y-axis. Keep smushing them. Okay. Oh, and I need negative. Can I go by 2s? Each line is 2. 2, 4, 6, 8. Making this negative 2. And then I'll do 1, 2. Plotting these points. 0, negative 1 is x is 0, y is negative 1, somewhere down there. X is 1, y is 2, something like this. I draw this line, let's see if I can pull it off. I realized I can move it, oops, earlier today. Something like this. Now we can do, and usually we label this line. So y equals 3x minus 1, or you can write L1 or something like that at one end of it, just so you can identify it. Line 2, when x is 0, y is 7, and when x is 1, y is 6. This gives me a rough idea. If I had a perfect grid, maybe I could get a better idea just by finding that intersection. But here, now we know. So now we see, oops, we see, I combined it into one word. We see the intersection should be somewhere kind of where x is between 1 and 2, but I did a poor job sketching, and maybe y is 5-ish, right? We see the intersection is around, let's say 1.5 x for the x and 5 for the y, roughly. This is just to get an idea of, does my answer make sense, right? Which is nice to check. Yeah. So, and this is your y equals negative x plus 7. I'm gonna add a page and bump these guys down. No. One thing you could try is what? At this intersection, right? Whatever the solution is, right? If you plug in x equals 1.5, then your y, once you solve it, should be 5. Kind of a giveaway in that case, right? And same thing here. Plug in x is 1.5, it should be 5. That's not true, right? So that's not the intersection. That's around where the intersection is. So what could you do, right? We can rely on the fact that, okay, at this point, right? The x's in both equations should be the same, and the y's in both equations should be the same. Now, what I like to do is, okay, if the y's for both of these are the same, right? So if this y and this y are the same, can't I just use them as a gateway, right? And I could say, okay, well, what if I rewrote this situation like this? 3x minus 1 is equal to y. And then next to it, I have y is equal to negative x plus 7. Now, if I had this a fancy animation, what would I do? I would kind of eliminate those y's, right? Because if this y is equal to this y, which is the intersection, right? That's the whole point of the intersection. Then saying that something is equal to y, which is equal to y, which is equal to something else, well, then this first thing has to equal the last thing, right? In math, we usually say if A is equal to B and B is equal to C, then A is equal to C. And that's the same property that we're using. Yeah. So here we kind of use this, and I just kind of smush them together. I'm imagining old school like PowerPoint changeovers where it's all like, but you can imagine it however you'd like. 3x minus 1 is equal to negative x plus 7 then. From here, the only variable I have is x, right? And so what could I do? I could solve for x, which is going to be very exciting, whatever this point is, right? We're saying, okay, when these two y's are equal to each other, x is this value. So let's solve for x. I'll say it here. Solve for x. I'll switch to just all the same color now. And to solve for x, I want to move all my x's to one side and all my non-x's to the other side, right? And so what I'm going to do is I'm going to add 1 to the right-hand side, and I'm going to add x to the left-hand side in one smooth move here, like that. 3x plus x is 4x, right? X is just 1x, so we get 4x is equal to 8. How's everyone feeling about this move? From 3x plus x to 4x. Okay. Good. That can take some work if it's been a while since you've done math. Solving for x from here, right? 8 divided by 4. So x must be 2. Which we already kind of figured out, didn't we? Just looking at this and saying, okay, well, we could have tried our way to points, right? And said, well, when I plugged in 1.5, it didn't work, right? 1.5, negative 1.5 plus 7 is not 5. Try another point, right? But we knew the realm that we were kind of aiming for. But now x equals 2, it just turns out that my scale is really bad. That's okay. So now we know at x equals 2, that's where we'll find the intersection. So now the intersection, and live it up, right? Grab a new piece of paper here. The intersection is at x equals 2. It doesn't matter which line you put x equals 2 into, but you want to make sure that they're the same. Otherwise, it's not the intersection, right? And so we use this to solve for y, and we can use line 1, y equals 3x, I think it was minus 1, yeah. Minus 1, so at x equals 2, I get y is 3 times 2 minus 1. Y is 6 minus 1 is 5. Which is kind of fun because that means my y scale was pretty good. Guess I did kind of use a ruler. Line 2 has to be the same, right? So we need to find that y is 5, otherwise we've done something wrong. So it's kind of a nice way to be able to check your work, right? And so y is negative x plus 7. Y is negative 2 plus 7, so that's the same as 7 minus 2. So y is 5. These values must be the same. Otherwise, it's not the intersection. It is not the intersection. So then the intersection is at x equals 2 and y equals 5. Therefore, the intersection is at x equals 2 and y is equal to 5, or as a point, 2, 5. Yeah. Nice. The way I solved it here is called the substitution method. Another common way that we can solve for the intersection is called the elimination method. So I want to show you that one next. Okay. It's called the substitution because I've essentially substituted this equation of the line in for y in the first equation. Right? But we'll be using the elimination method more, especially as we move into further chapters. So we'll focus there. But if you want to use this method, right, set them equal to each other, solve for x, figure out what the y is, that's fine by me. I'm okay with that. But the elimination method will pay off later. So a common algebraic method used to solve systems of equation is called the elimination method. The object is to eliminate one of the two variables by adding the left and right sides of the equations together. So once one variable is eliminated, then we have an equation with only one variable that we can solve for. One variable 4 can be solved. Well, not really, but I think we get it. That can be solved for, or some version of that. Finally, by substituting the value of the variable that's been found in one of the original equations, we get the value of the other variable. Very similar to what we just did. Okay, but I want to show you the difference. So I'm not going to draw the graph. You can imagine it. Right? You can use Desmos and you can find the intersection, but because it says the elimination method, you still have to show your work, but it's nice to be able to check your work. I forgot to do it for the previous one, but I'll do it for this one. Remind me. Find the intersection of the lines 2x plus y is equal to 7 and 3x minus y is equal to 3. So here it is in standard form, if you want to call it that. And the elimination method goes like this. If you have your 2x plus y is equal to 7, and then underneath it, making sure you stack your x's and your y's and your constants, right? We're going to write 3x minus y is equal to 3. And so making sure that you're stacking your your x variables, stacking your y variables, and stacking your constants. So if they're written in a different order, you'll want to rewrite them and match them up. Okay. So what we're going to do is we're going to be looking for something that we can do, adding or subtracting one of these rows from the other rows to eliminate one of the variables. For example, if I do this first row plus the second row, because I've got a negative here, right? Then I'm going to get rid of these y's, right? Because then I have y plus negative y. So this becomes, we're going to write it like this. So the goal is to eliminate one of the variables. Right? And you'll be allowed, we haven't done it here because we don't need to, but you'll be allowed to multiply by some number and then add or subtract rows. And with practice, we'll get better at it. But what you want to do now is you want to do 2x plus 3x, right? 2x plus 3x makes 5x. Y plus negative y makes 0. And that was the goal. Plus 0. Right? And then you don't want to forget about the other side of the equal sign. Even I do sometimes. You want to do 7 plus 3. 10. By eliminating that y, right, turning it into a 0, now I'm left with 5x is equal to 10. I can solve for x there, right? And so now solve for x. So I have 5x is equal to 10. So x is 10 divided by 5, which I'll just jump to 2. Now what? Now you can plug in x equals 2 into either of these equations, these ones, or if you prefer kind of these cleaner looking ones. I made a mess of these ones, right? They're the same. But if you plug in x equals 2 into either one of these equations, then you can solve for whatever y should be. And just like we saw earlier, right? If I plug in x equals 2 into the first equation, I should get the same y as if I plugged in x equals 2 into the second equation. So it's a good way of checking, right? Doing them both kind of side by side. So use x equals 2 to solve for y. I've got my first equation, 2x plus y is equal to 7. So if I plug in 2 times 2 plus y is 7. 2 times 2 is 4. Subtracting that from 7, I get y is equal to 3. How about the other line? Just to make sure, 3x minus y is equal to 3. If I plug in x equals 2, I get 6 minus y is equal to 3. 3 minus 6 is negative 3. Phew. You can just lob off a negative. Technically, you're dividing over by -1, But if you see a negative y is equal to -3, then y is equal to 3. Which is nice, because therefore the intersection is at x equals 2 and y equals 3. With some practice, that's going to be a little bit quicker, right, than the substitution method. But like I said, whichever way you want to find the intersection, as long as you understand that the at some point, the x and the y values will be the same for both lines, and that's the intersection, then I'm happy. And how am I doing? Oh boy. Make this bigger. Solve the system of equations. Sounds fancy, but all it's really asking you to do is find the intersection. By the elimination method. We're going to do the same thing, all right? Stack one on top of the other. It doesn't matter which order you do them in. Right? X plus 2y is equal to 3. And then underneath 2x plus 3y is equal to 4. I don't see a nice thing to do. Remembering the goal is to eliminate one of these variables, right? You can either do x minus 2x, that's not going to eliminate anything, but what if we pulled a fast one? And I change this to 2x plus 3y is equal to 4, and x plus 2y is equal to 3. Why would I do that? Because then I can do this. I can subtract 2 times the second row from the first row. All right, and so I'm allowed to multiply one of the rows by a number and then add and subtract. Okay. So being really careful. And if you want, you can distribute this -2x inside, right? Making sure that you get it on each of those 3 things, right? 3 terms. Right? And so here, let's see here. I'll make a note. You don't have to. If you're able to do it, then that's cool. But we can distribute -2, and we can have 2x plus 3y is equal to 4. And then I have -2 times x, and then this -2 also has to go on the 2y. So that means that -2 times 2 is -4. So then I have -4y. And then also on the 3, -2 times 3 puts me at -6. So now, once I've distributed it, it's easier because then I'm back to just adding the 2, right? Subtraction is just a special case of addition, right? You're just adding a negative coefficient. So now we're back here and we have 2x plus -2x. That was our goal, right, was to eliminate one of these, and you just kind of play around with it and see, okay, what could I manipulate to make one of these easy to eliminate? I didn't see an easy way to eliminate the y's, so that's when I started focusing on the x's. So 2x plus negative 2x is 0. 3 plus negative 4y, or 3y plus negative 4y, is negative y. And 4 plus negative 6 is negative 2. All of a sudden, we have y is equal to 2. Nice. That I can plug into. Let's do both. You only have to do one, but let's do both side by side. Good practice. Whenever you're plugging things back in, you want to do it in the original equations, right? Because if you're plugging things into something that you've reworked and manipulated, there's a chance you're plugging it into the wrong thing. So whenever you can, just go back to the very original equations. So x plus 2y is equal to 3. At y equals 2, I get x plus 2 times 2 is equal to 3. So x is 3 minus 4. I get negative 1. For the other equation, I'm hoping I get the same thing. 2x plus 3y is equal to 4. 2x plus 3y is equal to 4. 2x plus 3 times 2 is 4. So 2x is 4 minus 6, negative 2. So x is negative 2 divided by 2, which is negative 1. Phew. Therefore, the intersection is at negative 1, 2. Let's check it. Check our work. I know, tempting to do it beforehand. You could. Still have to show it all, so it doesn't matter. Okay, plugging in my equations here. X plus 2y is equal to 3. Okay, that looks good. And then 2x plus 3y is equal to 4. I realized I said it looks good before I even checked it. 2x plus 3y is equal to 4. Okay. Now, ta-da. And if there's an intersection, it'll highlight it with a little dot that you can click. We did it. Elimination method. Nice. Again. Let you think about what you've done. No, let you think about which one to eliminate. Let's start with 1 on top, and like I said, you're allowed to switch the order if it helps. Right, 4x minus 5y is equal to 6. Neither of these are lending themselves to elimination. What could you do? It's a pickle. Pickle for a nickel. Which one do you want to eliminate? X or Y? X. Let's do it. How? Let's force it. We will eliminate X. My go-to move is going to be deciding what I need to do to turn the coefficient of X into 1. I would need to divide by 4. I have to do it to the whole equation, right? That's going to turn it into 1. But then what can I do? Then I can multiply it by 3, right? So now it's going to be this kind of this chain where first I turn the coefficient of X into 1 so that I can manipulate it. And then I turn it into whatever I want so I can eliminate 3x in this case. Okay. So here, I'm going to say first, step 1, change the coefficient of X into 3, right? Ultimately, we want it to be a 3 for the second equation, right? Or I guess we could go the reverse, but we've been subtracting and adding the bottom row from the first one. So to me, it makes more sense to turn the bottom one into a 3, but it's the same method. So change the coefficient of X in the second equation into a 3. Okay, so then I have 3x minus 4y is equal to 5. And same thing, 4x minus 5y is equal to 6. But how am I going to manipulate this thing? Like I said, first thing I'm going to do is I'm only focusing on the 4, right? And I have to do it to the rest, but I'll deal with those consequences later. So now, what if I multiply by or divide by 4? Let's do that first. And then multiply by 3. Right. Dividing by 4 turns it into 1. Multiplying by 3 turns it into 3. And then subtract. And I didn't mean to make that one pink. I meant to write my note in pink. Turns 4x into x, and then turn x into 3x. We're gonna have to deal with some fractions here. So that's a bummer, but we can do it. Let's smush that negative fraction all the way through so it's nice and clean. Maybe not so clean. I keep writing the top row so that I'm always ready to eliminate at some point. So now, negative 3 over 4 times 4. This 4 over 4 is going to go to 1. So I get negative 3x. And then I'm going to be nice and careful here. Negative 5, I'll keep this negative 5 just so I don't lose the negative. And then I'm just going to write out for now negative 3 over 4 because I still haven't, oh, that's a y, got a feel for how comfortable you guys are with fractions yet. So until I know, I'll be careful. And that's equal to, negative 3/4 times 6. I'm inconsistent, aren't I? Sometimes I bump the multiplier inside. Usually if I have a subtraction, then I want to make sure that I keep that. And if not, then I put it on the left-hand side. But A times B is the same as B times A. Right? Okay, let's see here. Multiplying fractions. So now I have 3x minus 4y is equal to 5. I achieved my minus 3x because I forced it, right? But at what cost? Now I have to deal with this fraction. Okay. I have negative 5 times negative 3. That's going to be plus 15. Plus 15 over 4 times y. 3 times 6, 18. Let me see here, divided by 4. Still not nice. So I get negative 18 over 4. I'm going to try 15 over 4 is a nice decimal. Should we use a decimal? Skip the fractions. Otherwise, we'd need a common denominator. We'd have to rewrite 4 as 16 over 4. Let's not do that. 3x minus 4y is equal to 5. And then I have negative 3x plus 15 over 4 is 3.75y. And negative 18 over 4 is negative 4.5. Wouldn't it be so nice if this is where we started? We didn't have to go through forcing it all. We're building up to something that I would say is easier than this. Now we're ready. 3x plus negative 3x, right, is 0, our goal. Negative 4 plus 3.75. I'm gonna guess negative 0.25, but it's kind of late. So negative 4 plus 3.75, negative 0.25y. And 5 plus negative 4.5 puts me at 0.5, which means that y is at 0.5 divided by negative 0.25, which is negative 2. All that work for y equals negative 2? Come on. In the first equation, 3x minus 4y is equal to 5. Plug in y equals negative 2, I get 3x minus 4 times negative 2 is 5. Solving for x, I get 3x plus 8 is equal to 5, so I get 3x is equal to, oh, it shouldn't jump so far. 3x plus 8 is equal to 5. 5 minus 8 is negative 3, so x is negative 1. I'm getting lazy. Here we go. There. Let's check it in the other equation too, or as well. But I'll do it in the original. 4x minus 5y is equal to 6. Or x minus 5 times negative 2 is equal to 6. -5 times -2 is plus 10, so I get 4x plus 10 is equal to 6. So 4x is -4. That's a relief. Because I need them to be the same. So the intersection happens at -1, -2. Let's check it. Hmm. (3x minus 4y is equal to 5. And 4x minus 5y is equal to 6. Bump it over so I can see this thing over here. And somewhere at -1, -2, they intersect. We did it. Whoa, sorry. Yikes. That'll wake you up. Now you won't be able to sleep. Hey, it was supposed to have a screenshot of my intersection. I'm gonna need to retake that. It's defeating the whole purpose, but you were ready for it. I wasn't, but there. Defeating the whole purpose. There. Did it. That was a hard thing to do by elimination. It takes practice. All right, we'll pick up with the supply and demand equilibrium price next week. If you have any questions, let me know. Otherwise, have a great weekend. Don't see you till Tuesday. You got it.